Every single day, millions of developers around the world open up their terminals, type 11 simple characters, npm install, and hit enter. Within seconds, a magic progress bar dances across the screen. And just like that, a massive node_modules folder appears out of thin air, often weighing hundreds of megabytes and containing thousands of files you never explicitly asked for. To most of us, this is just a routine black box. We trust it, we wait for it, and we move on. But have you ever stopped to wonder, what is actually happening under the hood during those few seconds? How does npm figure out which dependencies to fetch? How does it resolve conflicting versions without breaking your app? And why on earth is node_modules famously mocked as the heaviest object in the universe? Welcome to Behind the Abstraction, the series where we rip open the black boxes of modern software engineering. Today, we're dissecting the complete lifecycle of npm install. It all begins with a single blueprint, your package.json file. You might think you're only installing 3 packages, say, Express, React, and Lodash. But packages have dependencies, and those dependencies have their own dependencies. This creates a massive structure known in computer science as a directed acyclic graph, DAG, or simply a dependency tree. In this first phase, npm performs recursive fetching. It reads your root package.json, requests the manifest file of every top-level package from the npm registry, and reads their manifests in turn. This brings us to a crucial mechanism, semantic versioning, or semver. In your configuration, you'll often see symbols like *1.2.0 or ~1.2.0. The ** symbol tells npm, give me any minor update that doesn't break compatibility. The ~* symbol restricts updates strictly to patch fixes. npm's resolution algorithm must evaluate every single version constraint across hundreds of packages to determine the exact, highest compatible version for every node in the graph. But what happens when 2 packages disagree on what version they need? Let's talk about resolution. Split screen animation, show a nested folder structure, old npm v2 versus a flat folder structure, modern npm v3 plus hoisting. Show a highlight on package.lock.json with a green security shield icon. Imagine package A requires Lodash at 4.0.0, but package B requires Lodash at 3.0.0. How does npm prevent your project from crashing? Back in the early days of npm version 2, the system used a strictly nested structure. Every package got its own private node_module subfolder. This led to massive duplicate files and deep file paths that literally broke Windows file system paths. Starting with npm version 3, npm introduced hoisting. The algorithm flattens the tree. It moves as many shared dependencies as possible up to the root node_modules directory. If 2 packages require compatible versions, they share a single copy at the root. If there's an unresolvable version conflict, npm falls back to nesting only the conflicting version inside that specific package's directory. This entire deterministic graph is then locked in place by package.lock.json. Never delete your lock file. The lock file records the exact version, registry URL, and cryptographic hash of every single package in your tree. It guarantees that when your code runs on your teammate's machine, or on a production CI/CD server, it builds using the exact same code byte for byte. Graphic showing a local disk cache, ~npm_cache. Data flowing from a CDN server versus data pulled instantly from local disk. SHA-512 cryptographic hash check animation. Now that the tree is resolved, it's time to actually get the code. But npm doesn't just blindly download zip files over the internet every single time. First, it checks your local disk cache, located in your home directory under ~npm_cache. If you've installed a package in another project recently, npm grabs the compressed tarball .tgz straight from your hard drive, skipping the network entirely. If the package isn't cached, npm fetches it from the global registry CDN. But before writing a single byte to your disk, npm executes a critical security step, the integrity check. Every package entry in your package.lock.json contains an integrity string, a SHA-512 cryptographic hash. npm calculates the hash of the downloaded tarball and compares it against the lock file. If even a single line of code was tampered with on the remote server, a classic man-in-the-middle or supply chain attack, npm aborts the installation immediately and flags an integrity error. Your local machine stays protected. B-roll of files extracting into node_modules. Zoom into the .bin folder showing symbolic links pointing to executable CLI tools like Jest or Tailwinds. Once verified, the tarballs are uncompressed and extracted directly into node_modules. But there's one more step before you can use CLI tools like Jest, Vite, or Tailwinds in your npm scripts. npm creates a hidden folder called node_modules.bin. Inside this directory, it generates symlinks, or symbolic links, pointing directly to the executable entry files defined in each package's manifest. This is why you can run npx tailwinds without having to type the full, ugly file path to the package deep inside node_modules. Finally, npm triggers lifecycle scripts. When a package is installed, it can define custom hooks like pre-install, install, or post-install. These scripts are executed natively on your operating system. While this allows packages to compile native C++ bindings, it is also one of the biggest security attack vectors in the JavaScript ecosystem. Malicious packages often hide malware inside post-install scripts to steal environment variables or SSH keys the moment you run npm install. Pro tip: you can use the ignore scripts flag when installing untrusted third-party packages to block this execution path. Summary infographic showing 4 main pillars. 1. Dependency tree, DAG. 2. Hoisting and lock file. 3. SHA-512 verification. 4. Symlinks and lifecycle execution. Outro graphics. So, the next time you type npm install, you'll know that in just a matter of seconds, npm has parsed semver and built a complex directed acyclic graph, flattened the dependency structure via hoisting to save disk space, locked down exact versions and verified SHA-512 hashes for security, extracted files, linked binaries via symlinks, and executed lifecycle hooks. Understanding this abstraction isn't just trivia, it makes you a better engineer. You now know why committing your package lock.json is non-negotiable, why hoisting can cause mysterious module not found bugs, and how to protect your machine from malicious lifecycle scripts. If you enjoyed peeling back the layers of everyday technology, hit that like button and subscribe. Drop a comment below. Do you use npm, yarn, pnpm, or bun? And what software abstraction should we dismantle next? Thanks for watching, and happy coding!